Our topic for today is going to be surface area. So we're still staying in our geometrical applications. So we knew we had the area. That was one of the first things that we learned about when we learned about integration. In fact, that's oftentimes how we think of integration. Sometimes we think about that too much, because integration is more than just area. It's really about finding the total. So surface area, we want to find the area of some three-dimensional shape. Now we're going to be very restrictive here. The kind of surfaces that we're going to consider are the kinds of surfaces when we do a rotation. So we're going to rotate a curve y equals f of x about some line, usually the x-axis or the y-axis, and that's going to form a shape. So we've talked about volumes of revolution. So today it's the surface area of that revolution. Now, if you want to do surface area of something more complicated that's not just a volume of revolution type shape, stay tuned. Calc 3, it's going to be great. Good stuff. But okay, so what do? Well, our ideas are always the same. We say, well, let's break things into little tiny parts and understand what's happening on each part. Now, if we think back to our last time, we talked about arc length. And we said, hey, we can break our curve up into little straight line segments. So we're going to focus on, at the start, imagine that we have just a straight line segment. So here's our straight line segment. And then we're going to spin it. And we're going to ask the question, what happens to that? What's the surface area of that? Because if we can figure that out, what we'll end up doing is we'll take our original curve, break into lots of small parts. We say, well, each part, when we spin it, it's like spinning a little line segment. So I can figure out what the surface area is for that, and then I add them all together. Now we can see that when we spin this, we get a fairly nice shape. And if you were to think about what the shape is, you can imagine extending this, and what you'll see is we're getting sort of a part of a cone. That's what we get when we spin a straight line segment, is a piece of a cone. Now, it might be that if our straight line segment is exactly parallel to where we spin, then it becomes a piece of a cylinder. That's a really special case, but it doesn't matter. It's all the same idea. All right, so our goal is to figure out what's the surface area of this thing. Okay, well, we're a lot better at just area. So what will we do? We'll reach into our pockets, and we'll pull out our scissors, and we'll do a little cut. Okay, so we cut, and then we're going to lay it flat. All right, so what happens when we lay it flat? Now, my claim is, when we lay this flat, we get something that looks like this. I call it a pizza crust shape. And my claim is, what it is it's like a part of a wedge of the circle. Now, it's not so hard to convince ourselves that this is what should be going on, because if you think back to what you have here, think about what the shape is. This is like a cone. So if I look at any point here, the distance to the tip of the cone, it's always the same amount. So any point on this edge is always equal distance from this center point. So this center point translates into that point right there. So it's always the same distance. And when you always are the same distance away, that means you're a circle. So when you take your outer part, that becomes this further circle away. The inner part comes this inner circle away. Now theta, well, it depends on how steep your cone is. Because you can have a cone which is very thin and narrow. Of course, you could also have a cone which is very thick. And depending upon the situation, that changes what your angle theta is. Now, at this point, you might be nervous thinking that we're actually going to have to find theta. But don't worry, we won't have to. Instead, we're going to use what we know about geometry. So we know a lot of things about circles because circles were studied since ancient times. Greeks loved circles. In fact, for them, the only two things that there were lines and circles. And so we know circles really well. So we need two straightforward facts. So one is how do you find the area? Because we are after finding the area of this piece. So the claim here is if I have a circle, so let's say this is my circle, and I take a little wedge, and I have an angle theta here. So this is supposed to be the center. How much area is there? Let's say this is R. Now, let's just figure it out. So what we can do is we can say, well, I know I'm after the area of the wedge, so I'll just call that area. And I happen to know the area of the whole circle is pi r squared. So if I were to divide, I can think of that as that's the ratio, or if you like, the percentage of how much area is in my wedge compared to the whole circle. On the other hand, I can think about I have an angle theta, and if I were to go all the way around, that would be 2 pi. So I can again look at that ratio, which is how much is theta compared to 2 pi. And now I say, aha, I can set these two equal to each other. And if you multiply both sides through by pi r squared, you get area equals, the pi's cancel, so you get 1/2 theta r squared. So that's where this formula is coming from. Now the other thing we need to know is this length. So suppose I want to understand what this length here is. Well, how do we do that? Well, the answer is we do the same thing. So let's just call this L. And now we'll say, well, L, that length that we're after, over the entire circumference. How much area is in the circumference of a circle of radius r? 2 pi r. So 2 pi r is equal to the angle divided by 2 pi. So now multiply both sides through by 2 pi r, and we get that length is equal to theta times r, which is that formula. So these are our two facts that we need to know, and if we have these two facts, then we're going to be able to figure out what's going on. So I want to label a couple of things here, just so we know what's going on. So I'm going to say that this distance, I'm going to call that r. Now in terms of what's happening over here, that would be this distance here. Now in some sense, that's the part we don't care about. What we really care about is this other length. And I'm going to call this L. Now the reason I'm going to call it L is because I'm going to think of it as the length of the piece. So I'm really going to think of this as coming from a length. And that's going to be really helpful for figuring out what the right formula should be. All right. So here's our goal. If we want to figure out this area here, I can think of it as take the big wedge, where the central angle is theta, and then the total radius is r plus L. And then I'm going to subtract out a smaller wedge. Central angle is still theta, but radius is just the r. All right, so here we go. Applying our formula, this is what we'll get. 1/2 theta times the quantity r plus L squared minus 1/2 theta times r squared. So far, so good. Well, we do one of our favorite things, algebra. There we go. So we have a square, so we square it. So we get the 1/2 theta r squared plus theta r L plus 1/2 theta L squared minus 1/2 theta r squared. And of course we're happy because we say, oh, look at those two terms, they cancel out. No surprise, that often happens when we do differences. So we get that the area is theta times r times L plus 1/2 theta L squared. Now comes the part where we say, what do we do? In the grand scheme of things, if we come back to our picture, we have two things, the theta times r times L and the 1/2 theta times L squared. Now here's sort of let's pause and think for a moment. Which term do we care about? Or rather, should I say, which term is sort of less important? Now this is not so obvious. And oftentimes one of the things you have to figure out is, okay, what can I safely ignore and what do I have to pay attention to? That's not a totally obvious thing to answer. But let's think about what happens in the limiting process. In the limit, what's getting small? Is it the r that's getting small or the L that's getting small? As we think about breaking things into smaller and smaller parts. It's the L that's getting small. So this thing right here, this is going to get, I'm going to call, this is a very technical term, very small. It's not just small, it's like small plus. You know, it's very small. So in some sense, that's the part I'm just going to ignore it and say that's my error, and that's going to get very small. And in the limit, that's going to go away. So now I'm going to focus on the theta times r times L. Now the thing that I do not like in this equation is the theta and the r. The L I'm okay with. The L, that's the length of a little segment. That's easy to find. But theta and r, that's not so obvious. So we'd like to find a way to get rid of theta and r. So have we seen something that looks like theta r recently? Well, we have seen. Yeah, the length. Oh, yeah, this is bad. I shouldn't use the same L here. Let me change this. All right, I'm going to edit. I'm going to change this to fancy L. There we go. There we go. Yes, fancy L is theta times r. Okay, so what is that? Well, theta times r, that's over here in this part of the picture. This is what L corresponds to. So I can replace theta r by that length. And now comes the question, what is that? Well, let's see what the paper says it is. And let's see if we agree. 2 pi times r of x times L. And our first reaction is, So the second term we just knock out. That's why it becomes an approximation. The approximation is because we're getting rid of this very small term. Now we have to think about what's happening. Well, the L comes there, 2 pi r of x. Where is that coming from? So let us step back to our picture here. This length right here came from this part of when we unfolded it. It came from this circle. So this is, even though it's part of a bigger circle, it also can be thought of as a part of this smaller circle here. Now we say, okay, so what's the length of that smaller circle? It's 2 pi times the radius. So what we're thinking of is that this length here, this is r of x. It's the height up on the inside piece. So that's where that 2 pi r of x is coming from, the circumference of that circle. So 2 pi r of x times L. Now, the last thing is the question is, what is L? Well, L, sorry, I'm going to keep coming back to this picture. L is the length of this line segment, which means we want to do a length. Do we know how to do length? Hint, we did it last time. It's the square root. So 2 pi r of x, square root of 1 plus f prime of x squared, and then delta x. Now you might say, shouldn't r of x and f of x be the same? To which my response is, not necessarily. It just depends on the situation. And we'll get into that in just a little bit. All right. So the grand moral is, we now have a way to find the area of this type of pizza crust shape. So, in other words, if I come and I were to say, I have this curve f of x, and I want to say how much surface area is there, and there's 2 pi times the radius times the square root of 1 plus f prime of x squared delta x. All right. So, this leads us to our lovely formula. We now know how to handle one small piece. And our philosophy says if you can handle one small piece, to get the total, you add all the pieces together. So our surface area is about what happens when we add all our pieces up. So we're adding up our individual parts. And of course, as we take a limit, our individual parts become smaller and smaller, which means that our approximation gets better and better. And so it goes to the correct value. The approximation becomes inequality. And so we have that the surface area, when we spin the curve f of x around some line, is found by taking the integral a to b of 2 pi r of x square root of 1 plus f prime of x squared dx. We should probably write down what we're doing here. Surface area spinning y equals f of x for a less than or equal to x less than or equal to b around some line. So f of x is the curve that we're spinning. The r of x is the distance to where we spin. So it just depends on context. If we're spinning around the x-axis, then the distance is the value of the function. If we're spinning around the y-axis, the distance to the y-axis is x. If we're spinning around a line, well, we vary it. It just depends on the situation. But it's good to be flexible. So the way I like to think about this, whenever I'm working on this is sort of the generic formula that I like to remember. So the surface area is the integral from a to b of 2 pi, and then there's a radius that comes here, and then there's the square root of 1 plus f prime of x squared dx, and I say, aha, this I remember, this came from the length formula. So I remember the length formula and say, okay, that goes on the end. And the tricky part is always to think about the following question. What's in the box? What's in the box? Because that varies. And how do you figure it out? The answer is you draw a picture. And you say, okay, if I want to understand, here's my curve y equals f of x, and I spin it, well, if I were to say spin it around the x-axis, then I think about I'm taking a little tiny piece, and the radius is how far I am from where I spin. So around the x-axis, what would my radius be? It would be f of x, because your distance here is f of x. Now, let's think about a different axis. So, different color. All right. Suppose I were to spin it around the y-axis. Well, now, I still have my little tiny piece. That doesn't change. I just say, how far am I from the y-axis? It's the x. So that's what would go in the box there. Now, I don't have to spin around an axis. I can spin around any line. We'll usually choose something horizontal. Suppose I was down here. Now, this is a line. Let's say it's the line y equals -2. I still have my little tiny piece. So now I ask the question, how far am I? So how far am I away? Yeah, it's f of x plus 2 more. And one of the ways you can think about it is you take a difference. You can say, well, it's how far is f of x from -2? Well, you subtract. So this would lead to f of x plus 2. That would be what r of x is. Now, of course, you might have something up here. Suppose this were y equals 3. Then, what would our radius be? What would it be? Someone has suggested f of x minus 3. Is that right? Someone has suggested 3 minus f of x. Is that right? Now you're like, okay, Steve, you're playing with us. That is correct. I am. Okay. Which one is correct? The 3 minus f of x is correct. And here's where you have to be a little bit careful. When you're doing something like the volume by the disk, you're squaring. And so it's very forgiving if you mess up on your sign. But here, you have to be a little bit careful and say, what is the sign? So oftentimes, the key is for this, you have to remember that there's the length part and then there's a radius. And if you're not sure what the radius is, just draw a silly picture and say, okay, I have my little tiny piece I'm spinning. How far am I from where I'm spinning? And that'll answer the question about what the radius should be. And we'll get some examples coming in here in the next few minutes. Oh, for example, right now. Find the surface area when y equals 2 root x for 3 less than or equal to x less than or equal to 8 is spun around the x-axis. Okay, so we have the curve 2 root x. So 2 root x does something like that. We're going from 3 up to 8. So something like that. We're spinning around the x-axis. So there's our x-axis. So that's where we're spinning around. So what's going to happen is that we're going to form some sort of interesting shape. Okay, so we're after the surface area of this shape. Well, the good news is we have a formula. In fact, the really good news is our formula is right next to us. So we can just refer to it. So our surface area, I'll call it surface area, integral, what are the bounds? 3 to 8, and we know that because they're right there, 3 to 8. Now, what will the 2 pi become? Yeah, it's 2 pi. Yeah, that's the easy one. Okay, now the r of x. So we should think of it as we have a little tiny piece. It doesn't matter whether you're integrating with respect to x or with respect to y. You always think of it, there's a little tiny piece that I'm spinning. How far am I from where I'm spinning? Yeah, you could think of it as 2 root x. You can think of it as f of x. You could even say y. And then I would say, well, that's because we need to know it. But yeah, you could think of it as y. That's perfectly fine. So that says that our radius here, our r of x, is the same as the function, 2 root x. So that's our radius. Then we have the square root of 1 plus. Okay, now we need to take that derivative. Well, what's the derivative of 2 times square root of x? Yeah, so this is 2 times x to 1/2. So when you take the derivative, y prime, the 1/2 comes down, cancels with the 2, you end up with x to negative 1/2, which is 1 over square root of x. So 1 plus 1 over square root of x squared dx. All right. Well, let's see what that becomes. Well, we can do a couple of not so hard things. For example, 2 pi times 2 becomes 4 pi. And we can combine the square roots together. So I'm going to think of this as the square root of x, and then it becomes 1 plus 1 over x. Because if I square that 1 over root x, that's 1 over x. So I combine those two square roots together. What's the next step for us to try? Distribute the x through. So 4 pi square root of x plus 1. Now, what technique do we need to integrate this type of function? Well, you could do u sub, or you could just say, I just know how to integrate this thing. The plus 1, in the grand scheme of things, it's basically, you can think of it as u equals x plus 1 if you wanted to. All right, people want to do u sub, we'll do that. But this is one you can probably do without doing u sub. So if you set u equal x plus 1, du equals dx. So this integral would become, what were the new bounds? 4 and 9. So you take the 3, plug it in, add 1, it's 4, take the 8, plug it in, add 1, you get 9. The 4 pi will become, that's right, and x plus 1 to the 1/2 becomes u to the 1/2, and dx becomes du. Integral of u to the 1/2, yep, u to the 3/2, because you add 1 and multiply by 2/3. Evaluate that from 4 to 9. 2/3 times 4 pi, that would be 8/3 pi. Now, 9 to the 3/2. 27. Now, the easy way to get that is to take the square root of 9, which would be 3, and then cube that. 3 times 3 times 3, which would be 27. 4 to the 3 halves is 8. And again, you can think of it, take the square root of 4, that would be 2, and then cube that. 2 times 2 times 2 is 8. 27 minus 8, 19. 19 times 8, a nice big number, yes. It's, what was it, 152? That sounds reasonable. We'll say it's 152. Is that right? 19 times 8? It's like 20 times 8, but then you overshot by 1/8, so you got to pull back. Okay, so that sounds reasonable. 152 thirds pi. All right, good. Easy, easy. So really, if we've done the arc length, this is not so bad. All we have to do is remember to get this little extra piece in front, and life is good. Life is good. Okay. So let's do another problem. Find the surface area when the curve y equals square root of 2 times x squared. The x squared is not inside the square root, so be careful here. The square root of 2 is just a number times the quantity x squared, plus e cubed for 0 less than or equal to x less than or equal to 1 is spun around the y-axis. All right. So that e cubed, strange. Well, it's not so bad. Really, what is the e cubed doing here? It's a shift. It's a vertical shift. It moves it up. Moves it up by a factor of e cubed, whatever that turns out to be. The square root of 2 times x squared, what does that look like? It's a parabola. X squared is a parabola. If I scale a parabola, it looks like a parabola still. So I have this parabola. Maybe I moved it up here. So here we go. There's the square root of 2x squared plus e cubed. And we're going from 0 up to 1. So this is the little piece that we're spinning, and we're spinning it around the y-axis. So there's where we're spinning. So the shape that we're going to form is going to end up looking a lot like a bowl, because it's a bowl. So that's a good reason why it looks like a bowl. Okay, so we have our basic shape. Good. Now, we just need to figure out our little individual pieces. On a side note, before we start, will this e cubed affect the answer? Let's just think about that. Should it affect the answer? No, because if you think about just the picture of what's happening here, if I move the e cubed is a vertical shift. But if I move this up and down, it's not going to affect the shape that is output. So e cubed should not affect the answer. So if somehow e cubed does affect the answer, it means we did something wrong. But our goal is to not do anything wrong. So we won't have to worry about that. Fingers crossed. Okay, so we start with our surface area. Now, let's see if you remember. It's the integral a to b of 2 pi, then something. And this is our radius. I always like to think about it. There's a box I have to fill in, and it's the square root of 1 plus f prime of x squared dx. Now, I should note that we're talking about surface area by taking a curve y equals f of x. There's nothing that prevents us from taking a curve x equals f of y. We do the same procedure. It's once you have the formulas in place, you just say, okay, I just need to figure out what's my arc length and pay attention to what's my radius. And so if you just understand the overarching generic formula and not memorize a bunch of special cases, you're in much better shape. All right, so that's it. That's what we need to find. So let's go through and fill in these pieces. What's a to b? 0 to 1. And we know that because it tells us 0 to 1. The 2 pi is the 2 pi. Now, the r of x. Again, Think of it as I have a little tiny piece. I know that's hard to see, but there's a little tiny piece there. How far is my little tiny piece from where I spin? Yeah, it's x. Because this little tiny piece, you can think of it, this is located at the point x comma y. So if it helps, just think of it as my little piece is currently located at x comma y. Where do I need to go? Well, I need to go over here, which is this line, the y-axis is x equals 0. So the distance from x to the line x equals 0 is x. All right, so that's good. So that's a little bit different from our last problem. So this becomes an x. Then we're going to have the square root of 1 plus. Now, what's our derivative? 2 times root 2 times x. And we're going to square that, dx. Well, all right, let's just go ahead and square it. If we take 2 times square root of 2, and if we were to square that, what would we get? You would get 8, x squared. Now, what do we do to integrate the square root, 2 pi times x times the square root of 1 plus 8x squared? We could use u substitution. What's a good u substitution to make? Probably, when we think of substitution, oftentimes we think of the inside job. What's the function on the inside? In our case, 1 plus 8x squared is what's on the inside. Okay, so we'll let that be u. u equals 1 plus 8x squared. What would du become? 16x dx, right. Divide, then we'll say that 1 over 16 du is x dx, and I happen to have an x dx. So life is good. What will the new bounds become? 1 to 9. How do you figure that out? You plug in the old bounds. You plug in x equals 0, you get 1 plus 0, which is 1. Plug in 1, you get 1 plus 8, which is 9. The 2 pi will still be 2 pi. The x dx will give us a 1/16 du, and then the square root of 1 plus 8x squared will become u to the 1/2, which is another way to say square root of u. Well, that's something we can integrate. In fact, we've just integrated that a few minutes ago, so we'll go ahead and integrate. The 2, by the way, in the 16 simplify to give us pi over 8. Then we'll get u to the power 3/2 when we integrate, and there'll be a 2/3 down in front. Evaluate from 1 to 9. Well, okay, I can give it a little bit of simplification with the 2 going into the 8. So we get pi over 12 in front. 9 to the 3/2, we said just a minute ago, was 27. 1 to the 3/2 is 1. 27 minus 1 is also known as 26. And now there's one last thing we can do. We can say, well, look, 12 and 26, they're both even. So divide that, we'll end up with 13 pi over 6. And that's our answer. Okay. An example. Set up, but do not evaluate integrals which find the surface area when y equals e to the x for 0 less than or equal to x less than or equal to 1 is spun around the following. So, So we have our y equals e to the x. So we don't need to sketch the whole curve. It comes along, hits here at 0, it comes up, and continues on. So I only care about this little stretch of the curve. So this is the curve we're spinning. Now our generic formula says what? Well, our generic formula says that our surface area is going to be the integral from 0 to 1 2 pi times something times the square root of 1 plus what goes here? It'll be the derivative, which is e to the x, and then I square e to the x. If you square e to the x, can you write that in a nice way? E to the 2x. That's e to the x quantity squared dx. If you had left it as e to the x quantity squared, you'd be fine. So we're not going to carry this integral out. And the reason we're not going to carry this integral out is it's not as fun as it looks. And if you don't trust me, you'll believe me by the end of next class. But we're just setting it up. So really, our setup is basically almost identical. The only thing we have to do is answer the question, what's in the box? And if we know what's in the box, then we're good to go. All right, so here we go. Let's do the y-axis. So again, I always think of that, there's just this little tiny piece I'm spinning. I'm just spinning that little tiny piece. Now, if I want to get to the y-axis, how far is the y-axis? It's x. And I should say, now, the answer to how far the y-axis is does have a small bit of dependence on how we're integrating. So currently, we're integrating everything in terms of x. So when you're integrating everything in terms of x, what happens is that your point, so for example, this point xy, when we're integrating in terms of x, we really think of it as x f of x. Now, if we had been integrating in terms of y, then what we would do, in other words, if we had x equals our function of y, then what we do is think of our point xy is really f of y comma y. So in our case, we are integrating with respect to x, so x is the right distance. So 2 pi x square root of 1 plus e to the 2x dx. All right, the x-axis. So that's this distance. How far is the x-axis? It's the y value, which is e to the x. So the integral 2 pi e to the x square root of 1 plus e to the 2x dx. X equals 1. So what does x equal 1? Let's draw that in. That would be this line. This is the line x equals 1. So how far are we from the line x equals 1? What's our radius? It will be 1 minus x. Right? Because here our x value is x. Here our x value is 1. And the difference is 1 minus x. Because I want the positive. I always want to think of radius as a positive value. Last one. Y equals 1. Well, where is that? That's this line. So how far are we from y equals 1? So is it 1 minus e to the x? Is it e to the x minus 1? Or is it something else entirely? It'll be e to the x minus 1. Because e to the x, that's where the y value is for my little piece. Here my y value is 1, and my little piece is above 1. So I want to take the larger minus the smaller. E to the x minus 1. All right, good. Now, our last fun thing for today. This is good. This is something called Gabriel's horn. So Gabriel is a famous angel in some cultures. So he has a horn. Now how do you form this horn? Well, we're going to take this curve y equals 1 over x. which is a very long curve. In fact, we're going to take it all the way to 1 to infinity, and we're going to spin this horn. So way out in infinity, that's where Gabriel is, and he's going to blow the horn. The question is, what is the volume in the horn? Okay? So we're spinning our region here. So our region, if we were to shade it, is a big region. Okay, so we're taking this whole thing all the way out to infinity, and we're going to spin that region around, and that's going to form a shape. And we're going to ask, what's the volume of that shape? So let's think about it. Now, this is y equals 1 over x. So I'm going to respect the problem. And by that I say, if it gives me y as a function of x, I'm going to think about integrating with respect to x. So I'm going to think about taking a very small slice, and I'm going to say, what happens when we spin this small slice? What shape are we forming? We form a circle. So what method do we use? We use the disk, which is a special case of the washer method. Okay, so this is disk, our washer method. So the volume, according to that, we'll write down the generic formula first, is a to b, then pi, and then it's the radius squared, and then there's a thickness. Okay, so that's our generic formula. In our case, what will a and b become? 1 and infinity. The pi? Still pi. The radius, okay. So that's the height. What's our radius? 1 over x squared. And the thickness is a dx. Just a small, thin part. All right, so what we have here is something that doesn't look so bad. So 1 to infinity of pi x to the minus 2 dx. What's the integral of x to the minus 2? Yeah, so add 1 to minus 2, you get minus 1, and then divide by minus 1 in the front, same as multiplying by minus 1, and then we're going to evaluate from 1 to infinity. If you like, this is minus pi over x from 1 to infinity. Now, we're going to plug in 1. Of course, when I say plug in, it's really plug in. You see, I'm putting those quote marks there, because we can't plug in infinity. But we can say, what happens as we go to infinity? That's what we mean when we say plug in infinity. What happens to 1 over x as we go to infinity? Goes to 0. So that says that when we plug in infinity, we get 0 minus, plug in 1, well, that's easy, minus pi over 1, giving us pi. Okay, good, good. Now at this point you're saying, fun problem, Steve. I had a lot of joy in doing this, but it has nothing to do with surface area. Well, that's because this has a part 2. You have the same horn. You're still going to spin it in the same way. And the question is, how much surface area? Okay, so this will be fun. All right, so surface area, a to b, 2 pi. Then we have our radius, what's in the box, the square root of 1 plus f prime of x squared dx. So let's fill this in. Integral from a to b. Well, a to b will be 1 to infinity, 2 pi. What's our radius? So we have a little tiny piece. How far are we? F of x, which is 1 over x. That's our radius. The square root of 1 plus, all right, what's the derivative of 1 over x? The derivative, be careful, minus 1 over x squared. Squared. Okay, So now we have to find the integral from 1 to infinity of 2 pi times 1 over x times the square root of 1 plus 1 over x to the 4th. Now at this point you're probably thinking that's a tall order, especially because we only have about 2.5 minutes left. All right, well maybe let's not try to find it exactly. Let's make things a little bit simpler on us. Let's do at least an estimate. What's one thing we know for sure about this value, the square root of 1 plus 1 over x to the 4th? What's the smallest it could be? 1. Right? So this is certainly at least as big as 1. Now you're probably not that impressed, but hold on. So this is at least as big as the integral from 1 to infinity of 2 pi times 1 over x. Now, can we do that integral? Yes. What's the integral of 1 over x? Natural log x. Okay. Now, plug in infinity, which of course means what happens to natural log as we go to infinity? It does what? As you go to infinity, natural log goes to infinity. So the surface area is at least as big as infinity. Well, there's not much room up there. So that says the surface area is infinity. Now, hold on. What's the punchline? Gabriel's horn. If we wanted to make it out of solid gold, no problem, because I only need a finite amount of gold, because it has finite volume. But suppose I had Gabriel's horn. I wanted to gold plate it, because after all, it needs to have something with gold. How much gold do I need to get to gold plate Gabriel's horn? Infinitely much gold. So you can make Gabriel's horn solid gold, but you can't plate it with gold. Math is fun. All right, have a good day.